Good afternoon. My name is Amin Vahdat. I'm from Google, and I'm going to be presenting the somewhat less exciting part 2 from Urs's presentation yesterday. Hopefully you'll still find I wanted to start by mentioning that the content of this talk really represents collaboration among a large number of people in engineering, architecture, operations, and deployment. I was going to try to list them all, but inevitably I would have left somebody off and felt terrible. Also, I would have had to fill up a couple of slides in a small font, and it wouldn't have been that meaningful. If you had to rank order the contributions of different folks to this effort, I certainly wouldn't have made the first page. So I feel really privileged to be presenting some of this material to you. So I'm going to skip most of the motivation. I think we've seen the fact that in the WAN setting, there's just a huge amount of bandwidth requirements, right? What you saw yesterday and today, for example, in the case of Google, is that Google runs about 7% of WAN bandwidth. And maybe more interestingly and more scarily for Google, the fraction of WAN bandwidth that Google runs is increasing over time. So that number might have been 5%, 3%, 1%. It's growing. So we need to be able to manage this and run it effectively, efficiently, and with high availability 24/7. These WAN unit costs are decreasing, and they're decreasing rapidly. Unfortunately, they're not decreasing nearly fast enough to keep up with the massive explosion in WAN bandwidth demands. So I'm going to categorize, you can come up with a bunch of different categorizations, but I'm going to categorize WAN cost components into 3 different places. There's the hardware, right, the routers, of course. As importantly, there's the transport gear that takes the output of these routers and actually puts them on fiber that runs across the world. Another big cost component actually is the amount of over-provisioning that you have to do, right? So, I mean, these router ports, these transport gear, this fiber is very expensive. And for fault tolerance, for maintaining your SLAs, for the fact that you can't really very easily differentiate your traffic, right? One kind of traffic might be more valuable than another. You basically have to over-provision dramatically to still deliver your 24/7. And then the third component, as important as the other two, is the operational expenses, the human costs. And this really stems from the box-centric view that we have of the network rather than the fabric-centric view. We heard just now about how we're moving toward virtual CLIs and really maybe affecting this shift where people aren't logging into individual boxes, but that really is a relatively recent shift. Okay, so why would we want to deploy a software-defined WAN? We want to be able to separate the software from the hardware. So we want to be able to choose the hardware that has the necessary features that we need and not more. Similarly, we want to be able to choose software based on our protocol requirements and not potentially every list of 100, 200 protocols that anybody could possibly need. A story I like to tell is that we have this paradox, at least for me, that the internet could not have gotten to this point without decentralization. Right? There was no way that we could have had organic, explosive growth without decentralization. Basically, plugging into the internet, at one point, you're now part of the internet. And now where we're at in 2012, I will claim that the internet can't get to where it needs to get to without centralization. So this is perhaps ironic, perhaps paradoxical. With centralized control, you can be more deterministic, you can be more efficient, and you can be more fault tolerant. Of course, it's not easy to get there, but I'll just give a very, very simple example, a cartoon example. If you have a distributed system with n components that wants to operate in basically fully decentralized manner, you need n-squared communication to sync your state, right? And basically have everyone know what everyone else is doing. That takes a long time. In a centralized system, you need 2n communication, right? One set of messages to the central coordinator, one set of messages back to all the different components. So inherently, with a bunch of work, of course, things can be much more efficient in a centralized environment. With a software-defined WAN, you can really push automation. You can separate monitoring, management, and operation in this fabric-centric view rather than a box-centric view. And finally, you can turn the crank on innovation much more quickly. Once you have the SDN basis, you can introduce new functionality and new features on basically software release cycles, what was referred to as push on green. Okay. So can we build a WAN that is more efficient, higher performance, more fault tolerant, and yes, cheaper, right? We want to figure out how we can deliver the internet to a global population in a cost-effective manner. So what I'm going to do here is go into a bit more detail on Google software-defined wide area network. cartoon picture of what our network might look like. We have a number of data centers spread across the world, and of course we have a number of edge sites where we peer with the rest of the internet, whether it's Deutsche Telekom or somewhere else. I'm going to be focusing on the network that interconnects the data centers together. And as was described yesterday, this network in terms of bandwidth demands is actually bigger than the one that connects the user-facing traffic. So we do have these two backbones, the I-scale one, the quote-unquote I-scale one that's internet-facing, and the G-scale one that has data center traffic. The two have very different requirements in terms of their topology, availability, and loss sensitivity, but also in terms of their traffic characteristics. So actually in the G-scale, the data center network, we have much more bursty communication patterns. It doesn't follow the smooth diurnal patterns that you might be used to in a typical ISP. Okay, and we've seen this picture as well. This is the interconnectivity for our data centers across the planet. I'll skip this. We had to, out of necessity, build our own hardware to deploy our software-defined WAN, just because there was no other way that we could deploy OpenFlow in the time frame that we were looking at. Okay, so essentially we took our hardware, and at the edge of our data center network, we interconnect this hardware together across the WAN. So now you can see the different components that I talked to on the hardware side. There's the routers, there's the transport gear, and there's the fiber. In this picture, we haven't done anything in reducing the cost of the transport gear or the fiber, but we have done something in reducing the cost of the routers. Now, if we can manage our network more efficiently, we can of course also reduce the total amount that we have to spend on transport gear and on fiber, just because we need less bandwidth. Right? If we don't have to over-provision dramatically, we can live with less bandwidth while still delivering the same SLAs to end customers. So we of course have to maintain pre-existing protocols, right? We have to both talk to the rest of the world with protocols like BGP, but internally, for us to actually deploy our system most quickly, the fastest thing we could do is run protocols like ISIS, like IBGP. We could run route reflectors, etc. Maybe we're not going to do this forever. Again, no comment on that point one way or the other, but we can and have to live in this quote-unquote hybrid world. I don't want to mix this with the working groups, but certainly we're living in a mixed world. So we might start with a picture like this. Right? We have our data center network, and somewhere at the edge of our data center network, we have a cluster border router. And now let's treat each data center network as an autonomous system in BGP speak. And this is speaking eBGP with a core network. Right? That's providing connectivity among data centers. So our cluster border router is peering with some number of switches, routers, at the edge, and these are then connecting across the WAN to other data center sites, using IBGP, ISIS for their internal connectivity between different data centers. Let's look at how we might, quote-unquote, upgrade this to an SDN. Okay, so first we're going to introduce some servers. So one of the benefits here is that we can remove some of the time-critical computation off of the embedded processors that run on these switches onto our modern server gear. And we might run a variety of different applications here. Quagga for BGP and ISIS perhaps, an OpenFlow controller, of course. Glue that might allow our OpenFlow controller to talk to Quagga and back and forth. Critical thing that I want to highlight here is some form of leader election, and that in our case is Paxos. So if we want to realize some of the benefits of SDN, we have to build fault tolerance in at every level. So that means that in whatever deployment you come up with, you need a robust leader election mechanism. And one hint I'll provide is that however number of instances you come up with for leader election, make sure it's an odd number and not even. There's a whole separate talk I can give on that topic. Okay, so now we're going to start running OpenFlow agents on a subset of these switches. And we can do this in standard ways, right? Upgrade half at a time at appropriate downtime, connect our OpenFlow controllers to these OpenFlow agents. Now we have something very interesting. We can still have half our network speaking, for example, eBGP to our cluster border router and ISIS to other wide area sites, just unmodified, no OpenFlow. The other half of our network, the other half of our switches are speaking eBGP through Quagga on a server, and IBGP and ISIS through Quagga on a server, coordinating the forwarding table entries on individual switches through the OpenFlow agents and through the glue that connects Quagga to the OpenFlow controller. Once we have some confidence in that, now note that we can do this at just one site. Right? We have our whole wide area network, but we don't have to be upgrading it all at once. In fact, even within a single site, we don't have to upgrade it all at once. So from the perspective of the data center and all the servers in that data center and all the applications that run in that data center, hopefully they see no difference, modular bugs or anything like that. Once we have confidence that the mixed mode is working fine, we can then upgrade that whole site to OpenFlow. Similarly, we can then move to a second site, a third site, and roll it out. Once we have that in place and we have confidence in our baseline SDN functionality, now what you can imagine happened to this point is we did a tremendous amount of work, huge amount of work, and saw no benefit. Okay, it's just running the exact same protocols as we had before. And now we're ready to introduce new functionality, like a traffic engineering server that can have a global view of communication patterns, etc. Okay, so let me go through some of the architecture here in a bit more detail. So with respect to traffic engineering and bandwidth allocation, so we have lots of different communication taking place on our data center. Some of it is more important than others. Right? Just naturally, you can imagine that we're running lots of applications with different levels of priority. So what we see in this picture is on the top left, something that basically is going to allocate bandwidth according to some business rules among different applications. And it's communicating through a collection mechanism. It is going and aggregating data from different data centers with respect to the communication to other data centers. And you can have different kinds of hierarchy and different kinds of aggregation that you might enforce here. It is collecting this information. It might even use rate limiters, right? It might say that you've hit your quota for Netflix in one analogy for the month, and I'm going to start enforcing some bandwidth limits. It might not. Regardless, it's communicating all the communication requirements between the data centers to a traffic engineering server, which might come up with a solution as to how bandwidth should be allocated and perhaps indirected, right, through non-shortest path forwarding now, through different sites. It'll use a software-defined networking API, right, through a gateway that we've developed that will then go ahead and affect basically the high-level policy that the traffic engineering server has come up with and program forwarding table entries in the end at the different sites to affect this. So I'm going to skip essentially the bandwidth allocation, but basically what you can imagine is that usage information flows up with respect to who's talking to whom and with what priority, and limits potentially are flowing down, and this is entirely optional. The key is that we use this to communicate global demand to the traffic engineering server. Right? So into the traffic engineering server, we have a demand matrix, basically saying this source, this data center, wants to talk to this other data center with this bandwidth. And there's a whole matrix, right? Rows and columns. Lots of different steps here, but we can then input this into a path allocation algorithm. I can now figure out, based on non-shortest path forwarding, how I can indirect my traffic through my whole network based on knowledge of the topology, right, and real-time knowledge of the topology. So for example, if there's a failure, that will flow up, go through the topology manager, and feed as input into this path allocation algorithm that I depict here. Through this process, essentially what we're going to get is a set of path assignments. Right? This source should talk to this destination with this path. Okay? And this can then now be programmed via the traffic engineering server through the software-defined networking API. Okay, so let's see what this might look like at each site. So we have, of course, an abstraction of what's going on in a particular data center. Right? So we have switches in data center 1. There are OpenFlow agents running on each switch. There are hardware tables, and different kinds of switches have different kinds of hardware tables. In this picture, I'm going to show you 3. An OpenFlow controller is running multiple switches through the OpenFlow agent, and it takes input from 2 different places. Routing, right, BGP and ISIS, and this is where the default shortest path information comes in that you would run without traffic engineering. And then there is a tunneling application that basically gets traffic engineering operations. So now let's imagine that we have 3 sites. Okay, the red circle here is the default shortest path forwarding information that we might have. And in this picture, I have site 1 wishing to communicate with site 3. So based on information that's coming from red, right, BGP, I might program my longest prefix match tables that says any traffic destined here, go ahead and forward it along the shortest path. Right? Any traffic that looks like this, send it along. I also have the green boxes, that's the traffic engineering side, that is keeping track of what's happening and perhaps going to enter information for non-shortest path forwarding. Right? So now I can use other hardware tables, maybe to enter information based on data from the traffic engineering server. Skip through this quickly. So while this is advancing, basically what we're going to do is set up incap through some hardware tables and decap through some other hardware tables to affect forwarding in direction through a second site. Right? So we've decided that some of the traffic should be indirected. Maybe it's not as high priority, maybe it's not latency sensitive through this second site. Okay. So what are some of the benefits that we can get? Here is one of our bigger links connecting data centers together. And what you can see over a 3-day period is that we run the links pretty hot. And we run them pretty hot on purpose. So the y-axis here is utilization. And of course, we're going at close to 100% utilization on purpose for a relatively substantial period of time. Typical WAN utilization levels, I understand from reading papers, et cetera, are closer to 30, 40%. Right? So what are the benefits of aggregation? Right? What do we get from running tunnels and in direction rather than working at the level of individual links? Basically, what this shows you is a factor of 6 reduction in WAN protocol exchanges that you have to have for tunnel changes relative to ISIS changes. Right? If you're not operating at the granularity of individual links, you have potentially big wins. Okay, and what this shows is that without traffic engineering, if you're just waiting for global reconvergence, you might have a long time, right? 9 seconds for global reconvergence to take place. With traffic engineering, the traffic drop period might only last a second. One question you might have is, what about fast failover? Certainly that's an option, but it's not guaranteed to be optimal, and it's not guaranteed to be correct. So it is very important to have the global reconvergence go much faster, and this is the n squared versus order n communication that I was talking about earlier. You saw this picture yesterday, and what I want to highlight is the amount of time that passed between when we were able to fully deploy the software-defined network and the time we were able to roll out centralized traffic engineering. Right? So once we paid, hopefully, the one-time cost and did the tremendous amount of work to get baseline functionality in place, we can now roll out new features much more quickly. And I'm done.
Oh, I was walking slowly for you. Okay, well then, we'll let Sachin go.